to you tonight about the subject of gravitational waves. So I've entitled this presentation "Gravitational Waves and Supermassive Monsters" because it is about gravitational waves, but it's also about the objects that generate gravitational waves. So just let me get myself sorted out here. So it was actually Albert Einstein who first came up with the existence of gravitational waves, and he saw them emerging from his equations of relativity, and just completely as if by magic, they just jumped out. But Einstein didn't really believe himself that gravitational waves existed. He spent 20 years wrestling with their existence, sometimes thinking, yes, they do exist, sometimes they don't exist. And in the end, he reached the following conclusion. And that conclusion was that gravitational waves do exist, but humans will never have the technology to detect them. It's not often that Einstein was wrong, as you probably know. But on this occasion, he was very wrong, because we do have the technology to detect them, and we have detected them. So the old idea from relativity is that there's this thing called space-time, and objects in space-time, any object with mass makes a depression, or if you like, a dent in space-time, in much the same way that a billiard ball would make a dent in a rubber sheet. And this was Einstein's great revelation from the general theory of relativity, that what we perceive as gravity is in fact the distortion of space-time. But another way of thinking about this is to think of the universe as a bit like a flat sea, where you have an object like a boat traveling through the sea, leaving a wake behind it, disturbing the sea, and these are your gravitational waves. Now, let's answer the question of what they are exactly. To do that, first of all, let's look at light. Now, I'm sure some of you will be familiar with the electromagnetic spectrum, going from long wavelength radiation on the left, at the radio end of the spectrum, with a very long wavelength, about the size of a building on its side, obviously. And then we go to the size of humans, down to the size of a honeybee. We go to the infrared, which are shorter wavelengths. We go into visible light. Then the other side of visible light, we go into the ultraviolet, the X-ray, and the gamma rays being the shortest wavelength of light and the most energetic. Now, all of this is known to scientists as light. But of course, the vast majority of this light we cannot see. In fact, if you actually look how much of the spectrum we can see, it's about that much. We can only see a tiny part of this electromagnetic spectrum. Our eyes are just not sensitive to anything else. So we're missing all of this light, apart from this tiny bit that we can see. As you may know, some animals like bees, for example, are sensitive to ultraviolet light. They can see ultraviolet light radiated by flowers, and flowers have evolved to do that to attract bees. And other animals can also see some other parts of this spectrum between the infrared and the ultraviolet. No animals, as far as I know, can see X-rays or microwaves or radio waves or gamma rays, but there are different animals that can see different parts of the spectrum. Now, this is all light, as I said. Now, if you imagine a diver in the sea with a big torch, that light beam is traveling through the medium. So there's a medium, in this case, that light travels through. Gravitational waves are not part of this at all, because they're not traveling through a medium. They are vibrations or waves in the medium of time and space itself. And this was Einstein's revelation. Now, there's a long history behind where physics was going at about the time Einstein discovered gravitational waves in the relativity equations. But basically, this is what they are. gravitational waves are tiny ripples in space-time itself. And what they do is that they stretch space in one direction and they squeeze it in another. So when a gravitational wave passes through the universe, it's this constant stretching and squeezing of space-time itself. I know this sounds crazy, but that's actually what it is. By the time they arrive at the Earth, these waves are incredibly, and I mean incredibly, tiny. And this is why Einstein thought we'd never have the technology to detect them, because he thought they were far too small to detect. So by the time the first gravitational waves ever detected reached the Earth, they stretched space by a billionth of a meter. Now, if you want to put that another way, it's 0 point that many zeros meters, or to put it another way, it's a trillionth of a trillionth of a trillionth the width of a human hair. This is how big these waves are. Or to put it even another way, about a thousandth the diameter of a proton, of course, being one of the particles that makes up the nucleus of an atom. So to detect these tiny, tiny, almost imperceptible waves in space-time, you need very, very special detectors, which we're going to talk about. Because of this stretching and squeezing of space, it means gravitational waves, when a gravitational wave passes, it changes the distance between objects. And on a very, very tiny scale, objects will alternately get closer together and then further apart again because of this stretching and squeezing of space-time. Now, these waves are very, very, very weak when they reach the Earth, as I've said, but some people have asked me in the past, but what if you were closer to the source? And one of the sources that we know about that generates gravitational waves is merging black holes. So if you were close to merging black holes, not so close that you would get pulled into the black hole, of course, but a safe distance away, if you were that close, could these waves do you any damage? Are they strong enough at the source to actually hurt you? Well, the answer is no, not really. But the thing that you can do is that you can actually hear them the closer you get to the source. So if we put an astronaut here, as the astronaut approached the source of the gravitational waves, these merging black holes that are spinning around each other at maybe 10% of the speed of light by the time they merge, you would first of all, or he or she would first of all hear a sort of a high-pitched ringing in their ears. And as they approach the source, that high-pitched ringing in their ears would get louder and louder and louder until it would become intolerable to listen to, this high-pitched, horrible screeching noise that would just make you want to, well, he can't obviously put his hands over his ears because he's in a helmet, he or she's in a helmet. But it would be really irritating, high-pitched noise that you just couldn't get rid of. The effect actually would be rather like listening to an Ed Sheeran album. As we all know, the best thing to do to an Ed Sheeran album is that. So the answer is that gravitational waves will never be strong enough to actually do you any damage, but you can, as you approach the source of gravitational waves, actually hear them. So what sort of objects create gravitational waves? Well, we've already mentioned merging black holes, but what we're going to do now is to get you to create some gravitational waves of your own. So what I want everybody to do is to put your arms in the air and start waving them backwards and forwards slowly. And I hope you all do this, because you can then tell people at work tomorrow that you've been creating some gravitational waves. So what you then do is make your arms move faster, and then faster, and then as fast as you possibly can. Hope everybody's doing this at home. Shame I can't see you, but I hope everybody's doing this. And then you can stop. And what you have just done is to create some gravitational waves, because every accelerating object in the universe creates gravitational waves. So you moving your arms faster and faster and then thereby accelerating will generate gravitational waves. The size of those waves depends on the mass of the object that generated them. But unfortunately, the ones generated by people are just too tiny probably to ever be detected. If you think how minuscule the waves are from merging black holes, the ones that you generate are absolutely much smaller than that, too small probably to ever be detected. So people just haven't got enough mass to generate gravitational waves that can be detected, even though some people have more mass than others, which is obviously true. However, let's look at the objects that do create gravitational waves that we can detect. So we are talking about the mergers of black holes. We are talking about the collisions of neutron stars. And fairly obviously a collision between a black hole and a neutron star. And also, with the evolving technology of gravitational waves in the future, it should be also possible to detect two supermassive black holes orbiting each other. Now, at the moment, the only black holes we can detect that are orbiting each other and then merging are stellar mass black holes. Supermassive black holes generate gravitational waves of much, much lower frequency that at the moment we haven't got the technology to detect with our existing gravitational wave detectors. But I'm going to come back to that because there's a caveat to that. I'm going to talk some more about that a bit later. We may be able to detect the gravitational waves from the accelerating matter in supernova explosions. Again, that's out of the range of our current detectors, but it should be possible within a few years to do that. We may also be able to detect gravitational waves from the beginning of the universe itself. And again, this is something I'm going to return to a little later. And as always, with any new branch of science, we may discover things that we never knew existed. So there may be completely unknown phenomena that we detect through gravitational waves. Let's have a look then. Let's turn our attention to how we detect them. So what I'd like to do is to introduce you to LIGO. LIGO stands for the Laser Interferometry Gravitational Wave Observatory, and this was the observatory that discovered the first gravitational waves in 2015. LIGO is in the United States. It consists of two tunnels, each of which is 4 kilometers long, and they meet at right angles in a detector building, if you want to call it that. And this is what it looks like from the air. But obviously, I need to explain exactly what's going on with this whole setup. So inside there, it's actually conceptually a very simple idea. You have a laser, and the laser fires a powerful beam at a thing called a beam splitter. You'll never guess what that does. That splits the beam. And then each one of the beams goes down each of the 4 kilometer tunnels till it reaches a very special mirror at the other end. And it bounces back to the beam splitter where the beams are recombined. And this happens over and over and over again. And then the resulting beam is then sent to a detector. And the only purpose of that detector is to detect the laser light. So let's see if I can just get this working to actually show you what actually happens. So we start with a beam. Hang on, is this actually going to work for me? Yeah, there we are. A gravitational wave hits the detector. This is greatly exaggerated, by the way. And let's see that again. Let's follow one of the beams through the beam splitter. It travels 4 kilometers down to the mirror, is bounced back, and meets the other one from the other end of the tunnel. The two beams are recombined and end up at the detector. Now, when a gravitational wave passes through the detector, that stretching and squeezing of space-time means the mirrors get further apart from one another. And as a result, the light comes in and out of phase. And what this means is the detector either sees light or not. In other words, that light is flickering. And it's this flickering of the light that the detector picks up, and therefore the LIGO team know that a gravitational wave has passed through the detector. As we said, the difference in distance between those two mirrors is measured as 1,000th the diameter of a proton. So as you can imagine, you need a very, very, very sophisticated piece of kit to detect that difference in distance. And this is why LIGO has been called the world's most accurate ruler. If you want to know what that would look like, that difference in distance that LIGO can detect, if you take the distance from the sun to Alpha Centauri b, which is 4.3 light years, it would be like having a ruler that could measure the difference of the thickness of a human hair over 4.3 light years. Now, I still cannot take that in. It can detect the change in distance of the thickness of a human hair over a distance of 4.3 light years. That's how accurate this ruler is. Quite amazing, eh? Well, there are two LIGOs in the United States. There's one in Hanford in Washington and in Livingston in Tennessee, and they are separated by a distance of 3,030 kilometers. That in light travel time, the distance light would take to travel between them, if you were to shine a laser from one to the other, would be 10 milliseconds. So light takes 10 milliseconds to travel from one LIGO to the other. Not that it does, but if you were to fire a laser beam between the two over 3,000 kilometers, it would take 10 microseconds. Now, we'll come back to that later because that figure is going to become significant a little later. The whole LIGO's facility is managed by the MIT on the East Coast, the Massachusetts Institute of Technology, and the California Institute of Technology on the West Coast. They are responsible for the management of LIGO. They developed it, they built it, and they manage it. But it's not the only gravitational wave detector. We have one in Europe, near Pisa, luckily well away from the tower, and this is called Virgo. And this is the European gravitational wave detector. It's now working in tandem with LIGO on the same observing runs. And why is that? Well, we'll come back to that again a little later. There's also a detector in Germany, at a place called Ruther near Hanover. This is the GO600 detector on a much smaller scale than LIGO. It's used mainly as a testbed for new technologies. So it's not actually an operational detector as such, but it's used to test. And the Japanese have built a gravitational wave detector called Kagra. This one is underground, shielded from earthly vibrations by a lot of solid rock. This is the world's first underground gravitational wave detector, and it too will join LIGO and Virgo's in their respective observing runs. So this is just some images of LIGO. There's one of the tunnels. And this is some of the optics inside one of the tunnels. Obviously, it has to be very clean. Everything has to be very clean because you're dealing with incredibly sensitive optical equipment. And there are two technicians there. Here they are repairing the microwave in the staff canteen. No, obviously not. This is a very interesting piece of equipment because what you've got to do, you've got to shield the detector from any vibrations on the Earth that you might mistake for gravitational waves. And this is part of a seismographic assembly to dampen any vibrations coming through the Earth so that they won't affect the detector. And it's actually a huge piece of equipment to dampen down everything, which it actually does. Now, just to show you what vibrations we're talking about, yes, we're talking about traffic vibration, we're talking about seismic vibrations, we're talking about the vibration of aeroplane jet engines coming from the sky, and this is the LIGO control room. Now, if you look on the right, you'll see that monitor, and I wonder whether anybody can guess what that monitor is measuring, what it's actually monitoring. Well, what it's actually monitoring is waves crashing on the beach 41 miles away. That's the signal of waves 41 miles from the coast. And that signal is big enough to completely upset LIGO's observations. So that signal has to be subtracted from what they're receiving at the detector. Any sort of vibration, if they know the waveform of it, if you like, they can filter it out. So they filter out all of these things: traffic noise, jet noise, seismic noise, the noise of breaking waves on the beach 41 miles away. All of this is filtered out, hopefully just leaving the gravitational wave signal that they're looking for. Let's talk about the first detection. Now, the event that generated the gravitational waves actually happened 1.3 billion years ago. And if you look at what was happening on the Earth 1.3 billion years ago, well, first of all, Keith Richards was born. And secondly, there was only, apart from him, there was only single-celled life on the Earth. So at the time this event happened, there was only single-celled life on the Earth, and Keith Richards. Now, let's have a look at what it actually was. So 1.3 billion years ago, there was a merger between two black holes. We know from the LIGO data that one of them had 29 times the mass of the Sun and the other had 36. Bear those figures in mind. We'll return to them. Also, each black hole was about 150 kilometers in diameter, and by the time they merged, they were spinning around each other at about 10% of the speed of light, so incredibly fast. And if you had been there 1.3 billion years ago, you would have seen something like this. The black holes have probably been orbiting each other for thousands, if not millions of years, but slowly getting closer together. And as they get closer together, they accelerate until they start generating gravitational waves. They get faster. This is much slowed down, of course. They get faster and faster and faster, and eventually they merge into one black hole. And at that point, the gravitational waves stop dead because nothing is accelerating anymore, so there's nothing to generate gravitational waves. Another way of looking at it would be to say, right, okay, so here you have the two black holes. One is smaller than the other. They get faster and faster as they co-orbit, and the gravitational waves get stronger and stronger and stronger until they merge and the gravitational waves just stop. The resulting black hole, according to the LIGO data, that the single black hole that was left after the merger has 62 solar masses. But wait 1 second. We said that each of those black holes that merged, they had 29 and 36 solar masses. And if you add those up, of course, you get to 65 solar masses. So somewhere we've lost 3 solar masses. Where did they go? Well, the answer is that that amount of mass was converted directly into gravitational waves as per E equals mc squared. So this was like taking 3 times the mass of the Sun, converting it to energy and pumping all of that energy into space-time in the form of gravitational waves. And this is why when two black holes merge, the resulting black hole never has exactly twice the mass of the individual black holes, because some of that mass is radiated away in the form of gravitational waves. Quite a thought. And that is a huge amount of energy. If you can imagine converting 3 times the mass of the Sun into energy, that's how much was put into space-time in the form of gravitational waves. So 1.3 billion years later, on September the 14th, 2015, the waves passed through the Earth, stretching it and squeezing it, as we were saying earlier. But of course, that means that they were also stretching and squeezing you by 1,000th the width of a proton. I don't know whether you actually remember that happening. No, of course you don't. But on September the 15th, 2015, You were stretched and squeezed along with everything else in space-time on the Earth, and the Earth itself, of course, by a thousandth the width of a proton for a few tenths of a second. But of course, that didn't end, because we are constantly being stretched and squeezed by gravitational waves arriving from all directions of the sky, from everywhere in the cosmos. And they are all the result of cataclysmic ancient events far off in the universe. So at the moment, you are almost certainly being stretched and squeezed by ancient cataclysmic events in the universe, which is quite a mind-blowing thought. That's not the best thing, though. We'll come back to that. At LIGO, the gravitational waves were detected at both observatories 10 milliseconds apart. Now, if you think what I said about the distance between the two LIGO observatories, they are 10 millilight seconds apart. I think I may have said microseconds earlier, it's milliseconds, but they are 10 millilight seconds apart. What did this demonstrate? That it took 10 milliseconds for the gravitational waves to travel from one observatory to the other. Therefore, gravitational waves travel at the speed of light. Now, Einstein thought that they probably did, but he had no way of proving it. But this demonstrated that what he said was correct, that gravitational waves travel at the speed of light. And here was the direct proof. And this is the historic first signal, the LIGO-Hanford data in yellow and the Livingston data in blue. And this is the actual signal, the historic first signal from a gravitational wave. And as you can see, it lasted just over half a second. The whole thing. Absolutely amazing. And we can go further. The way that physicists realized these were gravitational waves was to look at their waveform, because they had spent years running computer simulations of what black holes of different masses would look like when they merged. And they did countless thousands of simulations. And this is how they know what the mass of those black holes were, because they matched exactly one of the simulations. And the top two show the predicted data for black holes of 29 and 36 solar masses, respectively. And the bottom is the real signal. And as you can see, it's an almost exact match. Almost exact, because it will never be exactly the same because of differences in the equipment between LIGO Hanford and LIGO Livingston, tiny differences, etc., etc. But it's a match. I don't think anybody's going to quibble about that. So this was general relativity coming alive and showing us the merging of two black holes 1.3 billion years ago on this day in September 2015, demonstrating that gravitational waves do indeed travel at the speed of light. And here was the proof. Amazing. And we're actually going to listen to that 1.3 billion year old merging of two black holes. Now, the signals are very low frequency, so you're going to hear those. But what they've actually done as well at LIGO is shifted the frequency so that you can hear it better, because you can actually hear more detail in a higher frequency signal than you can in a lower frequency signal. And it's going to happen twice. So you're going to hear the original low frequency signal twice, then the frequency shifted signal twice, and it will repeat it twice as well. So let's have a go at this. Are you ready for this? You're about to hear the sound of two black holes merging 1.3 billion years ago. I hope everybody could hear that okay. Roger and Rachel, could you hear that okay?
Yes.
Great, thank you. Just want to make sure the sound was working okay. So There you have it. Now, there's something else interesting in this image, and that is this. Well, let's play it again. Why not? Now, do you notice on the right-hand side, do you hear the whoop at the end? That's known as the chirp. That chirp has encoded within it lots of incredibly useful information about the objects that generated the merger. And scientists are only just beginning to decode all the information in the chirp. That's the final fraction of a second when the merger actually occurred. And it does tell you, as well as from the simulation, we can tell the masses of the black holes that merge from that chirp and other information as well. So that chirp is incredibly important, and we're only now just beginning to understand what information it can tell us. And that's it. There's the chirp, as it's called. We'll come back to the chirp. We're going to talk about it in another context a little later. Now, where did this happen in the sky? Well, the problem with only two detectors is that you can't really triangulate where the signal came from in the sky. So this is a rough idea. This sort of banana-shaped colourful thing on the map of the sky, it happens somewhere in there. The brighter colours indicate where it was more likely to have originated, but it's not precise. This is why we need more gravitational wave detectors like Virgo and Kagra in Japan, because it will enable us to get a very, very precise location on the sky where the event happened. And then the astronomers can go and look at that point in the sky to see if they can actually see anything, whether there's any other radiation like X-rays or gamma or ultraviolet or anything emanating from that source. So it's important to build more gravitational wave detectors so we can actually triangulate on the sky and find out exactly where that signal came from. And then finally, on February the 11th, 2016, there was the announcement to the world that humans had detected gravitational waves. But it wasn't that easy. Between September and February, the scientists had to go through incredible processes to make absolutely sure that what they had detected was gravitational waves. And they tried everything they could to disprove the fact that it was gravitational waves, and they looked at every conceivable other explanation for it. And after several months of trying to disprove that they were gravitational waves, they couldn't. So this was the historic announcement to the world on February 11th, 2000.
Ladies and gentlemen, we have detected gravitational waves. We did it.
And of course, the world erupted. Well, the scientific world erupted. Probably didn't mean much to the man in the street or the man on the Clapham omnibus, as they say. But this was a momentous moment for science, an absolutely momentous moment. After decades and decades of working on what would become LIGO, here was the moment when David Retzer, the executive director of LIGO, could finally announce to the world, look, we've tried so hard to disprove that these are gravitational waves, but we can't. This is what they are. Amazing day. Absolutely amazing day. So, I'll just try and move. Here we are. I want to talk a little about the designation of these events because it's important to understand how they are designated. They have the main characteristic they have, or the main prefix they have, if you like, is GW for gravitational wave event. There are others, but I don't want to go into that at the moment because it gets a bit difficult. So they're given a designation of GW and then the date of the event being detected, which is given in the form year, month, day, good old American style. So GW 170817 was a gravitational wave that happened on the 17th of August 2017, just to tell you that. And LIGO and Virgo have produced an orrery of the first 10 black hole mergers. Now you're going to see each of these. If you look at the time at the top right of the screen, it's counting down until the merger, starting at 0.63 seconds. And as you can see, these pairs of black holes are different masses. And because they are different distances and they are different masses, each one generates a unique gravitational wave signal. So let's run this. And the first one is top left, the first ever detection. Very different signal from the others, depending on their mass and their distance. And then here we go with the time at 0 seconds, they merge. And here's the first one again, time counting down at top right until the merger. And that was the signal that we received, the first one. I won't go through all of these, but you get the idea. Each merger generates a unique signal depending on the mass of the black holes and the distance. But then we have the one I mentioned earlier, GW 170817. This was a very, very different event, and it quite took the nascent science by storm. Now, what we're going to do, if you look to the left of this, here are some of the the black hole merger signatures that we talked about, and notice their duration, some longer than others. GW 170817 didn't last fractions of a second; it lasted for nearly a minute, and therefore, LIGO scientists knew that they had something completely different. They had a different animal in the cosmic zoo that was not a black hole merger. Now, I'm going to run this. It's going to start very, very low frequency, but the frequency is going to rise, and you will hear it until it rises and rises, and you hear the chirp at the end. We're going to pick it up at the 30-second mark, 30 seconds into the signal, because before that, it would not be audible to human ears. So let's just run this, and you will actually hear this. Watch the time ticking away up to 35 seconds. You may begin to hear it now. 40 seconds. 45 seconds. 50 seconds. And at just under a minute, there finally is the chirp. This was the fingerprint of not a black hole merger. This was something different. What was it? Let's see if we can just give me 1 second. I knew this presentation would. There we are. This was a neutron star collision. This was the cataclysmic collision of two neutron stars. Now, let's just talk about the difference between what happens in a black hole merger and what happens in a neutron star collision. When black holes merge, there is no release of radiation other than gravitational waves. There's no explosion. There is simply a merger. And neutron stars, on the other hand, when they collide rather than merge, they actually create mammoth explosions that we refer to as kilonovas. GW 170817 was a kilonova explosion. Before we talk about the actual event itself, let's just do a quick bit of revision about what we know about neutron stars. Now, you may know that neutron stars are between about 1.1 to 2.3 solar masses in mass. They're, not much bigger than Manhattan, so they're tiny objects. But if you can imagine 2.3 times the mass of the sun crammed into something about the size of Manhattan, then you have an idea how dense these things are. And they are so dense, in fact, that 1 cubic centimeter teaspoon of neutron star material would weigh 1 billion tons. So take a teaspoonful of neutron star material, it would weigh 1 billion tons. That's incomprehensible to me, and I suspect it is to you as well. Moreover, their gravitational fields are so strong that they are 1,000 billion times the gravitational field of the Earth in strength, or trillion, if you like, I guess. So about 1 trillion times stronger than Earth's gravitational field. That's the gravitational field of a neutron star. If you were to drop a ball from a height of 1 meter onto an average 12-kilometer diameter neutron star, by the time the ball hit the surface, it would be moving at 1.4 million meters per second. So neutron stars are, along with black holes, the most bizarre and indeed dangerous objects in the universe. GW 170817 generated this signal. As we know, it was just under a minute in duration, so it definitely wasn't a black hole merger. Here's the signal from Hanford. Here's the one from Livingston. Oh, Virgo got hardly anything. This is a good thing, because there are certain areas of the sky that the Virgo detector in Pisa in Italy cannot see. And because it didn't pick up the signal, scientists knew that it was in the event had happened in one of the regions of sky that Virgo cannot see, so it became easier to find. But that wasn't the end of the story, and this is where it gets really interesting. So we received the gravitational wave signal. 1.7 seconds later, the orbiting Fermi Gamma Ray Observatory detected a burst of gamma rays coming from that area of the sky. 11 hours after the gravitational wave signal arrived, astronomers were able to track down the actual explosion itself and see it with telescopes in visible light, 11 hours after the gravitational wave event. 15 hours after the event, the orbiting Swift Ultraviolet Observatory observed a blast of ultraviolet light coming from the same location in the sky. 9 days after the gravitational wave event, the orbiting Chandra X-ray Observatory detected a burst of X-rays coming from the same point in the sky. And finally, there's the X-ray data from Chandra. That's actually the event there circled, the GW 170817 event. That's it in X-rays. And then finally, after 16 days after the gravitational wave event, radio waves were detected coming from the same event. Now, if you're asking why did all of these wavelengths of light from the explosion take different times to get here, think of this. The explosion generated a lot of debris, which slowly dissipated and cooled. And as it did so, different wavelengths of light could penetrate it at different times. So gamma rays were the first out, and radio waves were the last wavelength to escape that cocoon of debris surrounding the explosion. And that's why these wavelengths of light arrived at different times. And in fact, this is the radio data. If you look at what the arrow is pointing to, you can see the event brightening in radio waves, and finally after from 18 to 24 to 31 days. So that's the radio data from the kilonova of this cataclysmic neutron star collision observed first in gravitational waves, but this is the optical event. As you can see, this actually took place in a galaxy called NGC 4993, which is about 130 million light years away. And the inset animation shows you the explosion fading from the event on the 17th of August, and then fading. And within about 2.5 weeks, the explosion had faded all together. But this was not the most amazing thing. Astronomers were looking very carefully at the spectrum of this light, and what they saw happening was nucleosynthesis. This explosion was so violent, unbelievably violent, that it was generating new elements through the process of nucleosynthesis. So here are some facts about that explosion. At its peak brightness, that explosion that you just saw in the galaxy NGC 4993 was 100 million times brighter than the sun. Just think about that for a second. Again, this is something just incomprehensible to me. I can't even imagine what something 100 million times brighter than the sun would look like. So that was the brightness of the explosion. The forging of new elements happening before the eyes of astronomers through the spectroscopic analysis. And this nucleosynthesis, the elements forged in this incredible pressures and incredible temperatures, created, are you ready for this? 200 Earth masses of gold. And by my calculations, which you should never rely upon, but I make that 2,600 billion trillion tons of gold were created through nucleosynthesis in the aftermath of the initial explosion. But also 500 Earth masses of platinum, which works out to 6,500 billion trillion tons of platinum, were created through nucleosynthesis as a result of this explosion. What does this mean? It means now that we know where heavy elements like gold and platinum come from. They come from neutron star explosions, because it's long been accepted that your, if you like, common or garden supernova explosion does not develop the requisite temperatures and pressures to manufacture these heavy elements like gold and platinum. So if you are wearing any gold at the moment, or you have some gold jewelry around somewhere, or anything gold, look at it and think that was forged in the cataclysmic collision of two neutron stars countless years ago, probably billions of years ago, off in the cosmos somewhere. So the gold that we wear as jewelry comes from the collision of neutron stars. And this demonstrated what scientists have thought, that supernova explosions just aren't powerful enough to create these elements, these heavy elements, through nucleosynthesis. And also, during the explosion, the result of the two neutron stars colliding means that their combined mass pushed them over what's called the Chandrasekhar limit, and they collapsed spontaneously into a black hole because they could not support their weight. And as any weight big enough will do, it collapsed into a new black hole. We can't see it, of course, because it's black, but we're pretty sure that, according to the math, this is what would have happened after the neutron star collision. Maybe in just a couple of seconds afterwards, a new black hole was born. Amazing stuff, in my opinion. Absolutely amazing stuff. Now let's have a look at what we call the gravitational wave spectrum, which I like to say is like light, but shakier. Because in the same way that light has a spectrum, so does gravitational waves. We go from long wavelength to short wavelengths. At the moment, we are looking on the right-hand side about the 100 hertz frequency down to 1 hertz frequency, and we're looking at colliding neutron stars. We're looking at black holes. These are the things that we are able to observe. Now, also, if we move along, moving down in frequency to lower frequencies, 1 hertz to 10 to the minus 4 hertz, we see, first of all, things that may orbit supermassive black holes like neutron stars, because LIGO has actually detected collisions between neutron stars and black holes. They do happen, but these are supermassive black holes that capture neutron stars that generate low frequency gravitational waves. And maybe we can detect the first gravitational waves in the universe. We're not exactly sure at what frequency they will be found, but it's a possibility that with advancing technology, we'll be able to detect gravitational waves from the birth of the universe itself. And in 2034, Europe is launching LISA, which is the Laser Interferometry Space Antenna. It's going to be a mission to observe these frequencies and this I'll talk about LISA in a little while exactly, but with the LISA spacecraft, which is a spaceborne gravitational wave detector, we may be able to detect very, very, very ancient gravitational waves indeed, perhaps from the birth of the universe itself. If we then move down further to around 10 to the minus 8 hertz in wavelength, we have got something called pulsar timing. We'll talk about that in a little while because there have been some really interesting discoveries about that recently. And then going right down to 10 to the minus 16 hertz in wavelength, then we're looking at gravitational waves from the birth of the universe and maybe other things we've never even thought of. So this is the gravitational wave spectrum. At the moment, we can only observe wavelengths between 1 and 100 hertz, but with new technologies and space missions like LISA, we should be able to see a lot of other things in gravitational waves. Now, these pulsar timing arrays allow us to detect supermassive black holes, or rather the gravitational waves from supermassive black holes, with millisecond pulsars. How do we do this? Well, the first project to announce results from this experiment is called NanoGrav. It's sponsored by the National Science Foundation in America. And it's an experiment that's been running for 15 years. It's been observing for 15 years. How does it work? Well, you see, off in the galaxy, there are lots of pulsars. These are rotating neutron stars that shoot out beams of radiation like a lighthouse as they're rotating. And they've been looking at the so-called millisecond pulsars, which rotate extremely fast. The fastest yet observed rotates 767 times per second. So these are incredibly rapidly rotating neutron stars. And the idea behind this is that because they rotate with such a precise frequency, which we can measure, and that frequency rivals the best atomic clocks, they are so regular in their pulses that we know exactly how long their pulses take to reach the Earth. And the idea behind this is that if a gravitational wave passes through space, stretching and squeezing space-time, those signals will be delayed. And think of it like this. Think of a photon coming from one of those millisecond pulsars, and as a gravitational wave passes, it stretches space, so suddenly the photon has to travel a longer distance to get to the Earth and is therefore delayed. And by measuring these tiny, 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 tiny delays in the arrival of photons from these millisecond pulsars, that betrays the existence of the passing of a gravitational wave. Now, this is a worldwide project consisting of radio telescopes all over the world from lots of different countries. And here are some of them. You'll be glad to see bottom right that Jodrell Bank is a part of one of these pulsar timing arrays. It's worth saying that there are at least 6 different projects that have been working on the same thing. And when NanoGrav announced its findings a few months back, all of these projects had agreed not to release their findings before that. They had all found exactly the same thing, and NanoGrav drew the short straw to be the project that announced it. But there were different teams of astronomers working on this all over the world, showing yet again, as if we needed any more proof, that astronomy is a totally international cooperation. So, what did they find? After 15 years of observations, the NanoGrav project has detected a signal consistent with a background hum of gravitational waves emitted from binary supermassive black holes. Now, what this means is that there is this sort of background hum that the pulsar timing arrays have detected that match what we would expect from supermassive black holes, these low frequency gravitational waves. The results are preliminary and more observations are needed, but at the moment, that's what it looks like, because those signals match predictions of what such gravitational waves from co-orbiting supermassive black holes would look like. Almost. Annoyingly, the data fits, but not exactly. And astronomers, obviously, like any scientist, they hate things that don't match exactly because they are telling a story. And what the story is that we may be detecting gravitational waves from the dawn of time, that in fact they may not be coming from supermassive black holes. There's a possibility that they are coming from the Big Bang itself, which is quite a thought. We may actually be hearing the Big Bang. Now, when do the gravitational waves originate from? Well, let's go right back to the beginning of the universe, to what's called the inflationary epoch. I haven't got time today to go into exactly what that was, but I'm sure you can, if you Google the inflationary epoch, you can read all about it. It basically took place from 10 to the minus 36 to 10 to the minus 32 seconds after the Big Bang. At that point, we believe that the universe underwent some sort of phase transition. What do we mean by that? Well, an example of a phase transition is water turning into ice. It changes its state. And we believe that the universe went through some analogous transition at this point after the Big Bang. And that's called a phase transition. Now, if you think of how the universe was at that point, it was a fog. That's all it was. Light could not travel across the universe at that point because the universe was just simply too hot. And it took 380,000 years to cool until the point that light could travel across the universe. So the earliest light we have from the universe originates from 380,000 years after the Big Bang. Before that, photons that were emitted by particles were immediately reabsorbed by other particles because the universe was just too hot to allow photons to travel very far indeed. However, gravitational waves are ripples in space-time itself, and they do not have that problem. They could travel across the universe unimpeded by this fog. So what that would look like would be the fact that the gravitational waves are not bound by the conditions in the universe that stop photons traveling across the universe. These may be the waves that the pulsar timing rays have detected, which is quite an amazing thought. So to finish off with, let's have a look at the future of this amazing science. Firstly, LIGO India is in the process of being built. Yes, LIGO is setting up shop in India. They're taking the first preliminary steps of construction. It's going to be more or less a copy of the LIGOs in the United States at Hanford and Washington. So there'll be another gravitational wave detector coming online, which again will help track down where these signals are coming from exactly in the sky. LISA, the skyborne, I'll try that again. The spaceborne, sorry, it's been a long day. The spaceborne gravitational wave detector, consisting of a trio of satellites following the Earth in its orbit. And whereas the LIGO detectors have tunnels or arms that are 4 kilometers long, the LISA setup will have 3 satellites with laser beams firing between them that are 2.5 million kilometers apart in a triangular formation. This will allow them to detect very low frequency gravitational waves from things like supermassive black holes and the beginning of the universe itself. And it'll be 50 million kilometers behind the Earth in its orbit. And this is planned to launch in 2034. We'll have to wait and see. Also, Europe is building an incredible gravitational wave detector called the Einstein telescope. It's going to be built on the borders of the Netherlands, Belgium, and Germany in this area here. It's going to be underground to try and isolate it from any terrestrial vibrations, except seismic ones, obviously, that will have to be filtered out. And it's going to be an incredible project. It's going to involve 1,000 scientists from 20 countries. They're selecting the final site this year. Construction will begin in 2026 and will finish in 2035 when observations will start. But so what? Where does all this lead us? Well, the LIGO detection of gravitational waves is important for many reasons. And it really is an event as momentous as when Galileo first turned his telescope to the sky. Firstly, gravitational waves exist as Einstein predicted 100 years ago. Secondly, gravity does travel in waves. That was confirmed. Thirdly, gravitational waves do travel at the speed of light. Also confirmed. Heavy metals like gold and platinum are forged in neutron star collisions. Confirmed. It was our first direct observation of black holes. This, of course, followed a couple of years later. Our first visual image of a black hole came along in 2019, the supermassive black hole at the core of M87, of course. Confirmation that merging black holes and colliding neutron stars behave exactly, and I mean exactly, as predicted by general relativity. So Einstein, no surprise, was right again. It's the first time we've observed anything in the universe by something other than light. If you think about it, the only way we've ever observed the universe up until the detection of gravitational waves was through light. And now we have a different way of observing the universe. It's the birth of a completely new science, gravitational wave astronomy, and it's not often that you get to see the birth of a completely new science. So we should be thankful we're alive to see this. It's the birth of a new era called multi-messenger astronomy. Now, as the kilonova event GW 170817 demonstrated, we can now observe these events across multiple frequencies through gravitational waves, through X-rays, radio, ultraviolet, etc. And this has been called the era of multi-messenger astronomy. Each one of those wavelengths is like a messenger telling us a different part of the story about these cataclysmic events. And in a sense, we're now beginning to glimpse the inner workings of the universe for the very first time. And this inner working of the universe has been called the underverse. It's the engine under the bonnet, or under the hood if you're American, of course. We're beginning to see the inner workings of the universe. Up until now, it's been like trying to find out what's wrong with the car engine when we can't see all of the engine. We can see bits and pieces, but up until now, we've had no way of knowing how that engine actually worked. But now, we're beginning to see that engine slowly come into focus and understand what makes the universe tick. And the answer is gravitational waves. And if history is any guide, we're going to discover new things that we never knew existed, because every technological breakthrough in astronomy has resulted in us discovering things that we never knew even existed. This is an incredibly exciting time to be alive. It's a whole new era. And as somebody said, the universe is speaking. And now for the first time, we are listening to the underverse. And there's one final thought I would like to leave you with. If you did take part in that little thing earlier of creating your own gravitational waves, well, what happened to those waves? We now know that they moved away from you at the speed of light, but they're still going. And in fact, according to Einstein, and again, we have no reason to doubt him, gravitational waves never die out altogether. They get weaker and weaker, but they never die altogether. What does this mean? It means that every time you have done something that involved acceleration in your life, like walking down the street, putting your arms in the air, lifting a cup of coffee, you were writing gravitational waves into space-time, which will always be there. So, in other words, your whole life has been a tale of echoes. Now, sorry to put a dampener on things, Einstein didn't figure quantum physics into all of this, and we think there are quantum reasons why those gravitational waves will, in fact, not live forever, but they will certainly last a long time. So long after we're all dead, the story of your life in the form of gravitational waves will be traveling across the universe. And finally, and I promise you this is finally, if you want to know about the latest gravitational wave observations and be kept abreast of the latest gravitational waves events that have been detected at the gravitational wave detectors like Virgo and LIGO and CAGRA, well, there's an app you can download from the Play Store on your phone. It's called Chirp, believe it or not, and it will show you details about each gravitational wave event as it happens or very soon after it happens, with some of the details like where it occurred on the sky and other important information. All of the gravitational wave detectors are offline at the moment for upgrades. They should have come back online on March the 5th. We're still waiting for them, so, this is what happens with technology, but they'll be coming back online, I'm sure, very soon. And then you can be alerted whenever there's a new gravitational wave event that has been detected. And that is available at the Play Store and the iStore. And it's called Chirp, the gravitational wave information. And that's actually being managed by the University of Exeter. And we had a gentleman from the University of Exeter on Space Odysseys Live talking about this not so long ago. You can find that video on our channel, of course.